Okay, so now we're going to do a little bit of vector algebra. So there's two kinds of operations that I want to talk about first. One is called scalar multiplication, and the other one is called vector addition. And they both have, well, they're both really simple to compute, and they have nice geometric interpretations. So let's have, let's see, some toy vectors to play around with. Let's take vector u. We can describe this. Let's say this is 2, 3, and vector v can be 1, 4. All right, so scalar multiplication basically just means multiplying. So let's just see an example of that. If I wanted to multiply the vector u by a scalar, remember a scalar is just a number, what I would do is take the entries in my vector and exactly just multiply each one of those by the scalar that's out front. So the resulting vector would be 3 times 2 and then 3 times 3. So the coordinates, the new coordinates would be 6 and 9. So what are we really doing geometrically? So we start with vector u, 2, 3. So this is our vector u. And what we're doing when we multiply this vector by 3 is we're exactly stretching out the components by a factor of 3. So we started off with this vector 2, 3. If we multiply the x component by 3, instead of pointing at 3, we're going to be pointing at 6, and the y component is going to be 9. So we're going to be pointed up here. So this is our new vector, 3 times 2, 3. And it's just the same plain old vector stretched out by a factor of 3, pointing in the same direction. And it's easy to see that, right? Because remember that the angle was tan inverse of the length of the opposite side to the adjacent side. So in the first case, let's see, that would be 3 over 2. And that is, of course, going to be equal to tan inverse of 9 over 6, right? We just reduce the fraction, we get the same thing. So the angles are going to be the same. Just the magnitude is going to change by a factor of 3. Okay, so that is scalar multiplication. Okay, so now vector addition just means adding two vectors together. So we're going to take vector u and add it to vector v. So how does this work? Well, we have these two vectors, 2, 3, and vector 1, 4. And to get the sum of these two vectors, we're just going to add the x components, so 2 plus 1, and the y components, and that's going to be our new vector. Okay, so what's the geometric interpretation of this? All right, so we start off with our two vectors. So we have vector u points in the direction 2, 3, points in the direction 1, 4. Okay, so we can think of vector addition as basically describing a geometric process this way. So if we think about it dynamically, this is saying, okay, go from the origin to 2, 3, and then go from there to, to the end of this arrow, 1, 4, right? So, oops. So in other words, we're going to trace out this path. So we'll start at the origin, and we're going to follow vector u. And when we get there, we're going to draw a copy of v and go pretend this is the origin, and go right 1 and up 4. And so maybe you noticed that if we took another copy of u and put it right here, we'd make a parallelogram. And so that's why sometimes people call this the parallelogram method, because you're using those two vectors to become adjacent sides of a parallelogram, and then just kind of going from the origin all the way across the diagonal. Okay, so pretty simple. For vector addition, we just add component-wise. For scalar multiplication, we just multiply every component of the vector by that number. Maybe just one more word about these operations, all of the ones that we've talked about so far, and that is that everything works in higher dimensions. So if I have a vector w, say, that's supposed to be in three-dimensional space. Instead of having two components, we'll have three components. When I draw a picture, I'm going to have to draw it in 3 dimensions. So this says come out 2 units, go -1 in the y direction, and then go up 4. So 2, 1, and then up 4. We're going to end up with a point that points, with an arrow that points right about there. And the magnitude of this vector w, we can use that same distance formula, right, that in 2 dimensions we call the Pythagorean theorem, to compute the magnitude of w. This is going to be 2 squared plus -1 squared plus 4 squared. We can compute some angles, but we'll talk about that next time. And we can compute the sum of 2 vectors. So let's say, so if we have vector A, 3, 7, -10, we can compute W plus A. That would be 5, 6, and -6 in this case. And that parallelogram method works just fine with that too. The geometric interpretation is that we follow along vector W, and then we put a copy of A right after that, and we'd follow along that arrow. Okay, so this is just our basic vector algebra that we'll be using throughout the semester, and I think it's not too bad.